Here we're going to look at another technique for integration, and the motivation behind this one is to eventually solve what are called logistic differential equations. But in any case, it's a technique in its own right that we should look at, and it's based on a theorem that's a theorem from algebra, and it's written here, which is that if you have a rational function and the degree of the numerator is less than the degree of the denominator, and the denominator can be factored into distinct linear factors, then we can write the sum of the rational functions or as rational functions with distinct linear denominators. So that sounds like a lot of words whose meaning will be more clear when we do this example here. So notice f of x as written, it satisfies the requirements, right? The degree of p, the numerator, is less than the degree of the denominator, and the denominator factors into distinct, meaning different, linear factors. And so the claim is that when that's the case, you can split up this fraction into two fractions, a over x plus 1 plus b over x minus 3, where we determine the a and the b are yet to be determined. So the way you do that is you say, you look at this equation right here, and you say, well, the right side is two fractions, the left is 1. If you actually wanted to turn the right side into the left side, you would need a common denominator. So you would multiply the top and the bottom of this by x plus 3, and you'd multiply the top and the bottom of the right by x plus 1. And then what I want you to focus on is the relationship with just, so now these two fractions have the same, so let me just write that out. So this is a times x plus 3 plus, minus 3. I don't know where that plus came from. Minus. A times x minus 3 plus b times x plus 1. I'm really messing up left and right here. All over that common denominator, which is x plus 1, x minus 3. And so now what you do is you equate this 5x minus 3 with the a x minus 3 plus b x plus 1. So we can just focus on the numerators. That equation states that that 5x minus 3 is equal to a times x minus 3 plus b times x plus 1. So now we've got an equation. This is an equation that should be true for all x values. So there are certain ways you can do this. You can solve for a and b. That's what we're interested in. The best way to do it is just notice that this equation needs to be true for all values of x. So plug in x equals 3, because that will eliminate your a, or the a term. So when x equals 3, you get 5 times 3 minus 3, which is 12, equals, now this guy, a times x minus 3, goes away because it's a times 3 minus 3. And then you have b times 3 plus 1, so you have 4b. So that implies that b is equal to 3. On the other hand, when x equals negative 1, you get negative 5 minus 3, you get negative 8 equals, and this time the b term goes away because negative 1 plus 1 is 0. Negative 1 minus 3 is negative 4, so you get negative 4a. And so that means a is equal to 2. And so you're probably asking why this is useful at all. The reason it's useful is because so we essentially just figured out that we can rewrite, so let me just write down the original. All right, you're going to be faced with integrals like this, but that is much harder. So this is hard, as stated. That's a hard integral to do. Whereas this one here that we're writing, which is equivalent to the one on the left, So again, a was 2, so this is 2 over x plus 1 plus, and b was 3, 3 over x minus 3. This is easy. So we've turned an integral that's actually really difficult, at least as written, into one that's very, very easy. And the reason the one on the right is very easy is because the antiderivative of 2 over x plus 1 is just 2 natural log of the absolute value of x plus 1. And the antiderivative of 3 over x minus 3 is 3 natural log of the absolute value of x minus 3. Alright, so we took a problem that was really hard, as written, and turned it into one that was easy, and that's all because of this partial fraction decomposition technique. Alright, so you'll want to be on the lookout for these type of problems. So we'll do more examples in the next few slides. So let's use this technique from start to finish to evaluate this integral. So you've got a function here. It's a rational function. One thing you might want to try at the beginning is see if you can do a u substitution, just in general when you're doing kind of your decision trees for doing integrals. You might want to try a u substitution. I just want to point out here that if you try a u substitution, you'll run into, I want you to notice the instant where you see that this can't be done with u substitution. So the logical idea would be to let u be x squared minus 3x plus 4. So I'm going to put like the word sub here. And then du would be 2x minus 3 dx. Now the problem is that numerator, 5x minus 10, that can't really be replaced because we can't scale up 2x minus 3 into a 5x minus 10 because we'd have to scale the 2 up by 5. And when you scale that 2 up by 5, you'd be scaling the 3 up to 15, or to negative 15. So this substitution won't work here. All right. So that means we're going to have to use partial fractions. Using partial fraction decomposition. So that method requires that we split up 5x minus 10 over x squared minus 3x minus 4. And the claim is, since this factors, that factors into x plus 1, x minus 4, we can write this as a over x plus 1 plus b over x minus 4. And so then we would get a common denominator to turn the right side into looking like the left side. So I'd have to multiply the top and the bottom of this by x minus 4, and the top and the bottom of this by x plus 1. And then you just focus your attention on the numerator. So that would say 5x minus 10 is equal to a times x minus 4 plus b times x plus 1. All right, and then you make some intelligent choices for the values you plug in. Let's plug in 4. So when x equals 4, the left side becomes 20 minus 10, which is 10. The right side becomes 0 plus b times 5, so 5b. So that means that b equals 2. And when x equals negative 1, the left side becomes negative 15, and the right side becomes negative 1 minus 4 times a, which is negative 5a. So that means that a equals 3. So now we can rewrite our integral. So our original integral can be written in an easier form. So I can write this as 3 over x plus 1 plus our b was 2 over x minus 4, which equals the natural, or which equals which equals 3 times the natural log of the absolute value of x plus 1 plus 2, the natural log of the absolute value of x minus 4 plus c. Now, one last comment before we leave this behind. If you take AP, or if you're in an AP course, you may not, and this is like a multiple choice question, even though this is the right answer, and there's nothing wrong with leaving it like this. There, you can rewrite this using laws of logarithms, and you could rewrite this using this exponent property, moving that 3 up there, plus, and then moving this 2 up here. And the only reason I'm bringing this up is just so if you don't see the answer on a multiple choice, it may not mean you did it wrong. It may just mean you didn't express it in the way that they did. The other thing is when you square something, that's the same. Taking the absolute value and squaring it is the same as squaring it. So you may not see these absolute values on the right hand side. But the other thing is you can use the multiplication property, which would state that this is the same as ln of x plus 1, absolute value cubed, times x minus 4 squared, all within the log. So not the most important comment, but just if you're sort of fluent with those log properties, you'd want to be able to use those to rewrite an answer choice that you wrote down into one that you see on a multiple choice.